A great pleasure. Yeah, so it's a great pleasure to introduce the first speaker this morning, Fedor Sukochev, who is in Australia, in the University of New South Wales, in Sydney, and now in his place it's 11 p.m. So we are very grateful to him for giving his talk at this late time. And the title of his talk will be Quantum Differentiation and Integration for the Non-Commutative Plane. So Fedor, it's yours. Okay.
Thank you so much. It is a great pleasure to speak to all of you. And it is also sort of my debt of honor. So I feel it is something where I can finally pay back for all this inspiration which I experienced for so long, thanks to these great works in the non-commutative geometry and the cohomology theory. And I hope that I will also can entertain you and show to you something interesting today. So the first thing which I would like to explain will be the connection of my talk with a major theme of the conference, the cohomology theory and with the Cohn's character. It is, of course, very well known to everybody that Kohn defined a cyclic cocycle for the star subalgebra in the algebra of all bounded linear operators B of H as follows. So it is the trace, the standard trace on B of H, nothing else here. F is some self-adjoint isometry in the B of H, so F squared is identity. And then there is a product of two n commutators where A0, A2, and -1 are elements of this algebra. So those immediately when we look at this cocycle, cyclic cocycle, immediately the question is when this product, when the right-hand side makes sense. So we should have at least that this product should belong to the L1. Non-commutative L1 to the trace class. Okay, it's an obvious question. Well, let us now make further simplification, assume that all the elements A0, A1, and A2 and -1 coincide. So they're all equal to the same element A. And therefore, our equation reduced to the following question: when the commutator Fa belongs to the L2n. No, more generally, we can ask the question when the commutator Fa belongs to the Schatten-von Neumann class Lp for some p greater than 0. That's sort of the very, very basic question which anyone would ask when look at the cyclic cocycle. However, I will ask slightly different question, and it is very well explained how this question actually can appear. It was explained yet by Masoud Kalkali in his talk on the 30th cohomology theory, when he was actually explaining that when Kohn introduced the Hochschild formula for the Hochschild class of Chern character, then in fact, so to make this computation local for the character, we need that this commutator Fa belongs actually to the weak LP class, which I denote here LP infinity. And so the question which I will somehow motivating question for me is the following. So I start with the sum spectral triple. I take F, it is the signum of my D. We all think that D is a Dirac operator. A is some star algebra, but it is easier for me to speak when I take the A is a weak closure, so it is von Neumann algebra. And then I'm asking the question when this commutator Fa belongs to the weak class LP infinity. This may be rephrased as a question concerning quantized derivative, because on the left-hand side, what we have is what is called quantized derivative. So when the quantized derivative belongs to the class LP infinity. I will be discussing this question in the setting of commutative and non-commutative Euclidean spaces. Non-commutative Euclidean space will be denoted L infinity RD theta, but I will define it a little bit later in full. So let's start with the example. Consider a commutative situation first, one-dimensional commutative situation. Let's consider the algebra A as C infinity C of R, smooth functions compactly supported. H is L2 of R, and D is differentiation operator. F is, again, is signum of D. And then the following question, so how to describe the elements which are quantized. What will be the quantized derivative when the quantized derivative of element F belongs to the LP? Well, this question was, as you can guess, was considered in the classical analysis much before non-commutative geometry. And that was a classical result belonging to Vladimir Pella, who answered it in full, that this quantized derivative belongs to LP if and only if F belongs to some Bezov class. I will not define the Bezov classes. This is absolutely irrelevant to this talk. It's a famous space in the approximation theory. And you will see that it is also a little bit of exceptional example because it is one-dimensional geometries. It's sort of exceptional case. What will happen if we will go to the multidimensional case? Suppose it is not R, but RD, D strictly greater than 1. Suppose we look again at H is our L2 of RD. A is still the same algebra of all compactly supported smooth functions. And our D is now Dirac operator. So gamma k here are some gamma matrices. Dk's are partial differential operations. F is still signum of my Dirac operator. Well, again, the answer is very well known. It belongs to Janssen and Wolf. And it sounds like that this signum belongs to the LP when P strictly greater than D. D is dimension here. So D is fixed up to the end of the talk. It's dimension of my Euclidean space, even only if function F again belongs to this fancy Bezov class. And if P is less or equal than D, then if F is constant. Well, you see, somehow it's for the LP, the question is not particularly that interesting actually. However, there are the intermediate ideal, our weak LD, the ideal LD infinity. It sits between all LPs when P greater than D and all LPs when P is less or equal than D. And so the question is, let's ask the question when quantized derivative belongs to this class LD infinity. And that theorem was due to Kohn, Sullivan, and Telemann. I think it was 1994. And it sounds much more nicer than the result which I just cited from Pella's paper. So quantized derivative belongs to the LD infinity if and only if F belongs to the homogeneous Sobolev class. So homogeneous Sobolev class, it consists of all functions F such that nabla of F belongs to the LD of my space RD. That's it. That's a very, very kind of even aesthetically pleasing result. So somehow, I don't know, a little bit later, I will explain a little bit more. So that result was announced in that paper. So there was also the outline, how it should be proved. But a little bit later, we looked at this question again, and we gave a different proof in 2017 with a number of co-authors. And what I would like to emphasize was the idea, which again goes back to Alan Kohn in 1988, in a famous paper about this, where Dixmier traces were introduced, which I cite here. The next result shows how to pass from quantized one forms to ordinary forms, not by a classical limit, but by a direct application of the Dixmier trace. this one sentence actually, I think, contains a lot of interesting stuff in it. So let me try to explain possible approach through this sentence to the necessity direction of the theorem on the previous slide. So I wanted to prove that if quantized derivatives belongs to the weak LD class, then necessarily F belongs to the homogeneous Sobolev class. Imagine that we prove this formula. Imagine that we prove this formula in the middle. So what is on the left-hand side? This is quantized derivative. If it belongs to the LD infinity, then its power D belongs to the weak L1, to L1 infinity. On the L1 infinity, we have so-called Dixmier traces. And suppose for a second that we prove this formula, which I will later call conformal trace formula, that this trace on the left-hand side of this my quantized derivative is given by this formula. So these are partial derivatives of f. That's the integral classical RD in the usual Lebesgue integral. And then you look at this here. So this expression is just nothing but the Sobolev norm. Well, remember that Dixmier trace is continuous linear functional on the weak L1. And therefore, from this equality, I would immediately have that the norm of f in this Sobolev class is less or equal than the norm of the quantized derivative power d in the 1 infinity. And that's actually exactly half of the theorem. Of course, it still needs to be, this formula needs to be proven, but nevertheless, you see the main idea, how we can actually pass from the quantized one form by direct application of Dixmier trace. And that's exactly what I will be talking about today as well. So conformal trace formula, which, you know, again, when you just look at this formula, then I don't know, it's very aesthetically pleasing. So you have something what is now called quantized derivative. I compute the Dixmier trace of this quantized derivative. What do I have? I have the integral of the classical derivations of the function f. Well, okay, there's a square, there's d on 2, but kind of let us simply look at the main ideas which are here. So quantized derivatives can be computed in a way through the usual derivatives of f. It's fantastic formula. Now this formula is of course very similar, or it from the same family as the famous Const integration formula, which is a basis for the integration theory in non-commutative geometry. So what is this formula says? That if f is a compactly supported smooth functions on Rd, then when I compute the Dixmier trace of the product MF, 1 minus delta, delta is always Laplacian to the power minus d on 2, then what do I have? I actually reconstruct the classical integral of my function f. So again, aesthetically, it's something very pleasing. You take the multiplication operator, you compute its Dixmier trace in a way, and what do you reconstruct? You construct the integral. Before there was this conformal trace theorem, this is the classical trace theorem. Well, this is the motivation which I was looking for, which is going to explain what the results I'm going to present here. That will be similar theorems for non-commutative Euclidean space.
I ask about f. What is where f sits?
F, yes. Compactly supported function on Rd.
And okay, that's the only condition. Smooth and compact.
Nothing else. Nothing else. Nothing else. Yes. Nothing else. Well, now there will be a few boring slides with the notations. So first of all, B of H is always infinite dimensional Hilbert space. B of H is always the algebra of all bounded operators. For a compact operator T, mu k of t is the kth singular number, the eigenvalues of the absolute value of t. The sequence mu of t of those singular numbers, which are built in this decreasing order always, is a singular value sequence. It is another standard trace is always TR. It is, of course, also one of the great ideas which of Alan Kohn, which I learned, and which made me love the subject even more, because this is something here what also I think this word I read in Voiculescu, in non-commutative geometry of Alan Kohn, the ideals play the role of purveyors of infinitesimally small elements. I am an analyst in the depth of my heart, and I studied a lot of those non-commutative ideals, and to see that these ideals, Kalkin ideals and all of those stuff which coming from Kalkin and von Neumann, are in fact playing such an important role in non-commutative geometry, for me was personally a great pleasure. So LP infinity are always weak LP, which we can always understood as a principal ideals in B of H. What are the principal ideals? Are generated by the elements which are all zeros, except on the diagonal we have a sequence k plus 1 to the power minus 1 on. If p is 1, then it is simply the inverses of the natural numbers, and that will be Cwikel 1, non-commutative Cwikel 1. So these are infinitesimals of order 1 on p. It's the second notation. Finally, the traces. So the trace, what is the trace? The traces which we will consider in this talk are only the linear functionals on the Cwikel 1, L1 infinity. So what are the traces? These are unitarily invariant functionals on L1 infinity, or equivalently, these are functionals such that phi AB equals phi BA for every A from Cwikel 1 and for every B from B of H. I will say that trace is normalized if phi takes the value 1 on this sequence of 1, 1/2, 1/3, 1/4, 1/5, and so on. So on this, on the element which generates the principal ideal L1 infinity. The most famous traces are Dixmier traces. So what are the Dixmier traces? Dixmier defined them with the help of the generalized limits. So what is the generalized limit? It's a functional on the space of all convergent sequences with a norm 1. They exist by immediate application of Hahn-Banach theorem. The following definition is actually not definition, it's actually a theorem. And it says the following, that if I'll take an arbitrary extended limit, and if I'll consider the following mapping from the positive part of L1 infinity to the positive numbers given by that formula. So I compute firstly the sum of first n singular values. Well, this is the obviously the sum of those is majorized by log. So because it is the sequence of the inverses to the natural numbers, harmonic sequence. So it is less or equal than log n. So when I divide by log n, I have a bounded sequence depending on n. I apply omega and I get a number. It's of course a theorem that this mapping is a finite and additive on the positive cone of L1 infinity, and hence it can be extended to the unitarily invariant functional on the whole of L infinity. We'll call these Dixmier traces and we'll denote trace with the subscript omega. Now, you remember I already spoke about the cons trace. Const integration formula, const trace theorem. Yeah, that's the same, const integration formula, const trace theorem. Well, it is, again, it has a great predecessors in the classical analysis. In mathematical physics, people like Bierman and Solomak, and also Barry Simon and people around those groups, they started the question when the product of two operators MF, so MF is always a multiplier, times 1 minus delta to power minus d on 2 belongs to the weak L1. Well, of course, they did not really study exactly this one case of weak L1. They studied the case when this product belongs to LP, but I'm interested only in one question, when it belongs to L1 infinity. The result below probably belongs to Bierman and Solomak. However, for the proof, I will refer to the paper with Levitina, Sukochev, and Zanin. At the end of the talk, I'll give those references which I mentioned here. And what this theorem of Bierman and Solomak says, let us split RD into the cubes of unit length like this. So I take the unit cube, and then I shift this unit, I call it capital K, and then I shift it by number K from the ZD. Then I split an arbitrary function F on RD into those reductions on these cubes, on the unital cubes, compute the norms, L2 norms, and then I ask that the sum of all these norms is less than infinity. This space will be referred as little L1 of L2 on RD. And this theorem of Bierman and Solomak says that this product belongs to the weak L1 infinity. Again, you see, this is also one of things which also make you feel that what we are talking about is certainly of some of very, very important mathematics, because this question was started by in the classical analysis for generations, actually. Now the first result, which commutative result, it belongs to Zanin and myself, where we proved that under this condition of Bierman and Solomak, so if my function f is taken from L1 of L2 of RD, then we know, thanks to this Bierman and Solomak result, that this product belongs to the weak L1 class, and therefore I can compute the Dixmier trace. And lo and behold, I can not only Dixmier trace, I actually can take an arbitrary continuous normalized trace on the weak L1, and I still reconstruct the same integral of f. That's well, you see, of course, that this is an extension. That this is an extension of the original const result, where the function f was C infinity with a compact support. It's not that really that important that we obtain the generalization, but at very least this result gives us also some indication what I'm going to look further when I'll be speaking about a non-commutative plane. So this is the, say, precursor of the main results about the non-commutative plane. So that's the most general result so far for applications of const trace theorem for classical RD. Well, would be nice to have something like this also in the non-commutative Euclidean space.
Sorry, Fedor.
Please.
Just a question about your notation. I mean, you have L1 of L2 of RD, I see.
Right. Okay. Let's go back again. So let's have. I explained this, but you just left for that for that second. You left
for 1 minute. It's about the cube. Yeah.
Okay. My apologies to everyone. Okay, you don't have.
No. It's a pleasure. It's difficult to consume it straight away. So have a look. I take an arbitrary function on RD.
Okay, right.
And then I reduce it to the unital cubes. How these unital cubes are obtained? I take one unital cube, 0, 1 to the power d. And then I shift it by integers.
Okay, right.
So k runs through all these integers. So I look at the reduction on my function f at this cube for given k. I compute L2 norm. And then I sum up all these norms and I ask that this sum is finite.
See,
This is L1 of L2 of RD.
okay.
So yes, so if you compare with L2, then a square root.
Right.
So, I was trying to figure out what's the difference.
Right, right. So next, I'm now second one of those main results. As I said, in 2017, we undertook, motivated by this paper by Kohn, Sullivan, and Telemann, we wanted to give a complete proof. And so we presented this proof and have a look here. This is a slightly more general than I wrote on the slide 7. So the generalization came from here. It's also not that important, but the formula is now complete. So
it's much better because you make it local. I mean, by introducing the H. So no, it's
yes. Well, okay. Thank you. Yeah, it's localized now. Yes, so the formula become local. So it's a formula. Again, have a look. This is my favorite object, quantized derivative to the power d. This is now multiplied by an arbitrary h from L infinity. And then we have the formula that it is equal. This is still the same constant CD from the const formula. And that's our classical derivative. So nabla is the classical derivation of f. So that's the f, and f is an arbitrary from the homogeneous Sobolev class. So meaning that this integral is finite. So that's another definition. So when you think, if you are not everyday work with the Sobolev spaces, then this f belongs to this Sobolev class means that this integral is finite. So that's again, still we did not get yet to the non-commutative plane. Now we will go into this non-commutative plane. And of course, I will try to also move rather fast, because I presume in this audience, at least half of the audience know what is the non-commutative plane probably better than I do. But anyway, let me at least recall the ideology behind this object. So let us think about RD as an algebra. What algebra I would like? I would like to think about this algebra of the polynomial functions on RD. Okay, if I wanted to look at this, then so what is that? Then I will have D generators. They will be self-adjoint generators, xk equals xk star, and they of course commute because my RD is commutative algebra. So I have that's one of the way to look on the RD. Let's now make and change that this commutator between generators is not zero. Let us ask that this commutator become equal to the I theta k1 k2, where theta is d by d skew symmetric matrix. That's how I think about this non-commutative plane, but there are plenty of other stuff, and I will show to you how some few alternative ways of defining the non-commutative plane. So if I will think, so if I'll take this star algebra generated by those generators xk, which would be satisfying this latter condition, then we will call it non-commutative Euclidean space. Well, second slide, which explains slightly differently. Not nice to deal with unbounded functions, right? Polynomial functions are unbounded, not nice. Let us instead look at their exponentials. So for an arbitrary t in RD, let us consider the unitary operator u of t given by the exponential of this sum multiplied by r. A little bit of formal manipulations with a so defined u of t, and one could arrive to this formula that ut plus s is ut times us, and then there is this factor, unimodular factor. That's another way to look at the non-commutative plane through this unitary groups with this condition. The third way is even more precise and already concrete, very concrete. So let me give a formal definition now. So I will now simply consider the classical RD. Xi belongs to the L2 of RD. Theta is this matrix which is fixed. U and T are elements from RD. Then I'm defining ut of Xi by the following formula. By formula 1. Of course, one has to verify that this formula satisfies the formula for the group on the previous slide, but it's basically an exercise. Definition. Let's consider this group when T runs through the whole RD. Consider the von Neumann subalgebra in B of L2 RD generated by this group, and let's call it non-commutative Euclidean space and denote L infinity RD theta. This definition is good also because if theta is 0, then ut is simply translation operator. So there is nothing here, it's identity here. It's a translation operator, and L infinity RD 0 becomes what? It's become again L infinity of RD only in this format. It becomes the algebra of bounded Fourier multipliers on the L2 RD, not the classical multipliers, but the Fourier multipliers. Well, this slide actually says that this object is not interesting from the K-theoretical point of view. Indeed, suppose I want to introduce non-commutative Schwarz space on RD theta. How would I introduce it? I will consider the convolution of Ft when F is a classical Schwarz function with this group U of T. And I will call it the Schwarz function on the non-commutative plane. Well, this is motivated, of course, by the usual stuff. So because when you take the Schwarz space in the classical case and you close it in the uniform norm, you get C0 RD theta. So I'm simply mimicking this. What will be in this situation for when theta is non-degenerate? Well, in this situation, it happens that my C0 RD theta, so the uniform closure of the Schwarz space, is simply all compact operators. So C-star algebra is isomorphic to the algebra of all compact operators, and then it is trivial from the K-theoretical point of view. However, from the many other points of view, it's quite interesting. It's non-commutative manifold, non-compact manifold. That's makes life much more harder here. L infinity RD theta, whatever it is, actually happens to be even simpler object. It is in fact isomorphic to the B of H. Since I ask that my matrix theta is antisymmetric and non-degenerate, it means that D must be even, and therefore D divided by 2 is integer. So the algebra L infinity RD theta is star isomorphic to the B of L2 RD theta. Now, in one of our papers, we build a spatial isomorphism between this algebra and RD theta, and therefore, in this case, what should be the natural semifinite trace? Well, it is obviously the usual trace composed with this spatial isomorphism. In this situation, non-commutative LP spaces become simply the classical Schatten von Neumann LP classes. So tau theta is.
I have a question at this moment.
Please.
So for the abstracts are isomorphisms, in fact, the dimension of RD is irrelevant, yes, but you want this isomorphism to be somehow canonically defined from this data, yes, and then you
yes.
By 2, yes.
Yes.
Okay, thank you.
Because I defined in a very concrete way in a very concrete way, I define non-commutative plane. And exploiting this concrete definition, how I put it in here, I could build a spatial isomorphism.
I see.
And then I can get this trace. Now,
okay.
Now the partial derivatives. Well, you remember that if my theta is 0, I just said that in this case, my classical L infinity RD becomes simply bounded Fourier multipliers. Because here, in this format, in this definition, we are actually on the Fourier side of this. And therefore, our partial derivatives becoming simply multiplication operators. So the nabla is simply the collection of D commuting self-adjoint operators, those multipliers, and obviously Laplacian will be given by this formula. Now I'm coming to the definition of non-commutative Sobolev spaces. So with every x from the non-commutative Euclidean space, L infinity RD theta, I can now consider the commutators. Suppose it happens that x is such that the commutator is bounded. Then it will again belongs to this L infinity RD theta. Then I could consider the repeated commutators. And I could write the partial alpha x as those repeated commutators, provided, of course, they exist, provided they belong to this L infinity RD theta. With this definition of those repeated commutators, I can now speak about the Sobolev, non-commutative Sobolev spaces of RD theta. So what are those? We fix, say, some indices P and M. What we are asking that the norm P's, of course, these are non-commutative LP norms. Remember, these are Schatten-von Neumann LP norms, which such that the sum of all of those commutators, so all of these commutators, when degree of alpha is less or equal than M is fixed, it must be finite, and then that's the definition of this inhomogeneous because alpha equals to 0 is allowed. Inhomogeneous. Homogeneous when alpha is strictly greater than 0. And so these are our non-commutative Sobolev spaces. Okay, I still have time. Now I'm coming now to state the two final main results which underlie all of this talk, and you will see that one result is very similar to the classical one, and the other one is very different. So firstly, let us come back to this Cwikel estimates. So Cwikel estimates, the name of Cwikel, this was the question of Barry Simon to describe when in the classical situation of the classical space RD, when this product, so X should be MF, falls into the some weak LP class, P greater than 2. So that's why how this in the literature this name is associated with this kind of estimates. It's quite popular in mathematical physics actually. So well, okay, so we're coming to this question. Suppose I take X in L1 RD, and I wanted to know when this product belongs to L1. You remember that I cited the result or to L1 infinity, you know. So you remember the classical result was about this space L1 of L2 of RD, but we don't have anything like that in the non-commutative Euclidean plane space. I could not put non-intersecting cubes there and split RD into this union of those cubes. Not possible. All right, so the first result is as following. Suppose X belongs to this homogeneous Sobolev class, which I just defined on the previous slide, then this product belongs to the weak L1 infinity. I still think that this theorem is quite consistent with the classical case. Why? Because we have a Sobolev embedding theorem, which allows with this space is actually subspace of L2. So when you look at this, then you see when you still feel that there are still this strong connection, even though, as I said, there is no way you can decompose this non-commutative Euclidean plane into this union of cubes. Well, okay, so we have belonging to the L1 infinity, this Cwikel estimate. So now it is time to get applied the trace. All right, so this is this first main result. So second to last main result. So if I have X belonging to non-commutative Sobolev class, and if I have an arbitrary continuous normalized trace phi, then Kahn's trace theorem in this non-commutative setting holds. Of course, you see, this is especially interesting. This is just, you remember, tau theta is the trace on B of H. So it's a classical standard trace in my interpretation of non-commutative plane, right? If my theta is 0, then actually all of those things simply collapses back to the classical integral, and it will be equal to this number, to the classical Lebesgue integral. So that's, to my mind, is quite satisfactory extension of the classical result from the plane to the, well, to the non-commutative plane. It remains to discuss the question with which we started. What about the quantized derivatives? How the formulas for quantized derivatives look like from the very beginning? The one I started. Well, first of all, let's recall how we should introduce the Dirac operator on the non-commutative plane. How we will define? Exactly in the same way how we define the classical Dirac operator on the commutative plane. So you take the collection of gamma matrices, so anti-commuting Clifford generators, you take the products with the partial derivatives, you take their sum from 1 to d. That's Dirac operator for non-commutative plane. F is the signum of Dirac operator. And then I'm having the classical Fredholm module for, say, C0 RD theta. You remember this will be just compact operators, nothing else. F is this one. And then again, we are faced with a legitimate question: what will be the formula for quantized derivative? That's the last result of this talk, and the last main result of this talk, which says the following: that if X belongs to the inhomogeneous Bezos space, then quantized derivatives falls into the LD infinity. That's expected. This is very, very similar to what was in the commutative case, Cohn-Sullivan element. But have a look now at this formula. That's a genuine non-commutative effect, which we have here, and which is resulting. So S d minus 1, the unit sphere, d-dimensional, d minus 1 dimensional unit sphere, unit ball. Tau theta is the classical trace in the definition of our non-commutative plane. Dj are our partial derivatives. Sj, Sk's are elements from the components of this. S is belongs to this unit ball. So S is a S1, S2, and so on, Sd minus 1. So and then the formula becomes like this. Why this formula? Well, okay, how to explain to you that this is the different. This is, if again I'm going back to commutative situation, if my partial derivatives dk and dj all commute, and then theta is simply the usual integral, then this formula will collapse to the classical formula like this one, 1-to-1. But as I said, in this situation, when the partial derivatives do not commute, this is really something quite different from everything I've seen in this area before. That was my last slide. Let me quickly list the papers and my collaborators, to whom I'm very grateful. So it is Cwikel estimates, this is joint paper with Levitsina and Zanin. Then the results about classical Pond's formula are done in the papers with Zanin for commutative and non-commutative plane. But the last result about the quantized differential and non-commutative Euclidean space, this is the joint work with McDonald and X.Xiong. And that's about it. Thank you for your attention.
Thanks a lot. Thanks a lot, Fedor. Thanks a lot for this.
Thank you very much.
Yes. Yes. I mean,